Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And ignition and liftoff of Ares-1X, testing concepts for the future of new rocket design.
Altitude now 2 miles. Vapor pressure now tapering off as designed. The vehicle is aligned itself with the planned trajectory. We've passed Mach 1 and we're now passing Max Q. We have our Max Q system ID maneuver PTI engaged. Now passing Mach 2. Vehicle now 10 miles altitude, downrange distance 8 miles, and a velocity of 1,540 miles per hour. Plus 80 seconds, we've started our supersonic large amplitude ID maneuver PTI. We see the response. We started the last PTI maneuver, structural mode ID, and we passed T plus 105 seconds. Vehicle's now traveling Mach 4, 20 miles altitude, downrange distance 32 miles. The SRM tail-off is observed. Burnout. Our APUs have shut down. CRDs have shut down. BDM fire. And SEP. We show a SEP and a tumble motor ignition. And we can also confirm on video. We see both parts of the vehicle tumbling, the first stage as well as the upper stage. Successful separation. Good clean signal all the way. T plus 150 seconds.
Ares-1X was the first stage prototype and design concept demonstrator of Ares-1, a launch system for human spaceflight developed by the National Aeronautics and Space Administration. Ares-1X was successfully launched on October 28, 2009. The project cost was $445 million. It was the first launch from LC-39B until Artemis 1 13 years later. The NASA Constellation program's exploration missions will include an Ares-1 crew launch vehicle, an Ares-5 cargo launch vehicle required to place crew and cargo in low Earth orbit. Crew and cargo transportation systems required for human space travel, and transportation systems and scientific equipment required for human exploration of the Moon and Mars. Early Ares-1 configurations will support International Space Station resupply missions. A self-supporting cylindrical structure, the Ares-1 upper stage will be approximately 84 feet long and 18 feet in diameter. The upper stage element is being designed for increased supportability, reducing the logistics footprint, and increased reliability to meet human rating requirements imposed by NASA standards. The design also incorporates state-of-the-art materials, hardware, design, and integrated logistics planning, thus facilitating a supportable, reliable, and operable system. With NASA retiring the Space Shuttle fleet in 2010, the success of the Ares-1 project is essential to America's continued leadership in space. The first Ares-1 test flight, called Ares-1X, is scheduled for 2009. Subsequent test flights will continue thereafter, with the first crewed flight of the Crew Exploration Vehicle, Orion, planned for no later than 2015. Crew transportation to the ISS will follow within the same decade, and the first lunar excursion is scheduled for the 2020 timeframe. The Ares-1 upper stage is being designed by a NASA design team and fabricated by the upper stage production contractor, the Boeing Company, at Michaud Assembly Facility in New Orleans, Louisiana. NASA awarded this contract to Boeing in August 2007 in a competitive procurement as part of an agreement that includes the assembly, checkout, and delivery of the completed integrated upper stage. NASA also solicited for an upper stage instrument unit avionics contractor to fabricate, assemble, and check out the avionics hardware and systems into the instrument unit. The agency awarded this contract to Boeing in 2007. The upper stage office at Marshall Space Flight Center is responsible for the upper stage design, development, test, and evaluation, including project management, development planning, resource planning, tracking, and risk management. The USO is also responsible for the qualification acceptance of flight hardware. NASA will maintain data rights for the design and resulting upper stage hardware. The DDT&E period consists of the first 5 test flights of the Ares-1 through Ares-1X, Ares-1Y, Orion 1, Orion 2 crewed, and Orion 3 crewed. The USO deploys a low-cost strategy that maximizes price competition and emphasizes total cost of ownership early in the design cycle. Safety is also emphasized in all phases of design and production. The upper stage will provide the guidance, navigation, and control, and the Saturn-derived J2X upper stage engine will provide the thrust and propulsive impulse required for the second stage of the Ares-1 ascent flight after the first stage separates from the launch vehicle. The baseline design reference mission calls for the upper stage to provide active thrust via the upper stage engine for approximately 463 seconds after the first stage burnout and separation. Shortly after upper stage engine cutoff, the Orion crew escape vehicle separates from the upper stage and ignites for insertion into low Earth orbit. The upper stage is dormant after safe shutdown of the upper stage engine and re-enters for disposal in the Indian Ocean. The 2 design reference mission trajectories envisioned for the Ares-1 launch vehicle are 28.5 degrees flight profile to support lunar missions and a 51.6 degree flight profile to support ISS missions. The upper stage element is responsible for delivering a certified avionics system for the Ares-1 during all program phases of ground processing and flight. This responsibility includes all supporting ground infrastructure, facilities, hardware, and software necessary for design, development, test, checkout, and production. The UI will be the primary location for the avionics systems. However, some avionics will be located in other areas of the upper stage, including the aft skirt, interstage, and thrust cone. The avionics system is composed of all electronic hardware required for ground processing and checkout, as well as in-flight vehicle guidance, navigation, and control, command and data handling, and pre-flight checkout. The final integrated Ares-1 upper stage will be the product of numerous partnerships among industry participants, the USPC and IUAC, and multiple NASA centers. The development process begins with component tests and advances to more integrated testing as the design matures. The design is managed in design analysis cycles that provide coordinated decomposition, detailed design at the component level, and reintegration of the system. The design analysis cycles are scheduled to support design reviews. Development of the upper stage is a partnership between MSFC, Kennedy Space Center, Glenn Research Center, Langley Research Center, Ames Research Center, Stennis Space Center, and Johnson Space Center. MSFC has the project management and development responsibility, and MAF will be used to manufacture and assemble vehicle hardware. The project also works closely with a number of aerospace and manufacturing industry leaders. In 2007, the upper stage element successfully completed a systems requirements review and system definition review. The SRR, completed in April 2007, confirmed that 1. The upper stage element requirements were complete, verifiable, properly flowed down and traceable, validated, allocated to the subsystem level, and ready to be placed under configuration control. 2. Associated risks were identified with mitigations. 3. The requirements were responsive to mission requirements, and the architecture design concept could fulfill the mission objectives within imposed constraints. And 4. The upper stage element was of sufficient maturity to warrant moving forward to the next phase of development and the SDR. Upper stage subsystems, including avionics and software and main propulsion system, have also successfully completed their respective subsystem SRRs. The SDR, completed in October 2007, evaluated the element level design against the current set of baseline element requirements. The upper stage team openly presented and discussed actions and forward work to close out all upper stage SDR pre-board findings, with the board concurring on proceeding to the upper stage preliminary design review. The requirements phase is followed by the preliminary design phase, which will be completed in August 2008 with the PDR for the upper stage element. PDRs for each of the upper stage subsystems were completed in May 2008. Subsystem components are being fabricated and procured during this phase to support the development phase, design and test activities. Upon completion of the PDRs, the element will enter the final flight design phase, culminating with the critical design reviews in November 2009, at which point the upper stage flight configuration design will be baselined. After completion of the CDRs, flight configuration hardware fabrication to support component level design qualification testing, systems level design qualification, and flight system fabrication and assembly will begin. All flight configuration hardware, including all qualification hardware, will be fabricated to release drawings. The current version of the Space Shuttle's external tank uses a 2195 aluminum lithium alloy, which can be welded and withstands fractures to a temperature of minus 423 degrees, the temperature at which the liquid hydrogen propellant is stored on board. The Ares-1 upper stage will use aluminum lithium alloy tanks with external insulation to contain the liquid oxygen and liquid hydrogen propellants. The upper stage UI, thrust cone, and umbilical plates will also be fabricated from aluminum lithium 2195. The upper stage common bulkhead will be manufactured from aluminum lithium 2219. An innovative self-reacting friction stir welding process used successfully on the shuttle's external tank project will also be used on the Ares-1 upper stage. Friction stir welding transforms the aluminum lithium alloy from a solid state into a plastic-like state, and then methodically stirs the materials together under pressure to form a welded joint. The advantages of using the self-reacting friction stir welding process include the ability to join materials previously considered unweldable, and the improvement of properties relative to the fusion welding process. Self-reacting friction stir welding also has the added advantages of requiring simplified tooling and no anvil, and has the potential for lower defects and faster travel rates than conventional friction stir welding processes. Additionally, a robotic weld tool at MSFC is now welding test panels for the Ares-1 upper stage. Once startup issues are resolved, welding of sample ET dome gores will begin and will serve as a high-fidelity checkout of robotic operation. Follow-on operations will include installation of the upper stage dome welding prototype tooling and welding of the gores and Y-rings for manufacturing demonstration and structural development test articles at MSFC. The first foam spray at MSFC in support of the Ares-1 upper stage has also been completed. The system was set up to develop and qualify thermal protection foam for application to upper stage cryogenic systems. Because the Space Shuttle Heritage Foam System was chlorofluorocarbons that will be outlawed after 2015, the upper stage foams will use non-ozone depleting blowing agents. The next steps for this facility are to screen candidate materials, then develop the best candidates for the various applications on the upper stage. The results should be thermal protection systems materials with environmentally compliant components. Ares-1 upper stage structural development test efforts are also continuing for small panel aluminum lithium buckling tests. The purpose of these tests is to characterize the behavior of compression-loaded orthogrid panels for strength and stability, as well as correlate through the analytical approaches with the instrumentation data and photogrammetry. Testing is similar to previous testing performed by Lockheed Martin of MAF for the Shuttle ET project. Test support equipment from the previous testing of ET panels was modified to support this test series, which was established as developmental. There are no program or qualification requirements to be verified, to provide lessons learned prior to initiating future test series involving large panels and flight qualification test articles. The structural test plan for these initial test cells for 5 monocoque panels to be tested by applying a comprehensive load through the test fixturing until a failure is identified or a maximum load is reached, or the test requester stops the test. A successful test is one in which the test article is loaded to failure or maximum load and data was obtained for correlation purposes. This testing is conducted in the Gilmore Universal Test Machine in the Load Test Annex extension at MSFC, and will be followed by composite panel testing, common bulkhead development testing, and interstage and IU qualification testing. In addition to structural development testing, the upper stage structures and thermal subsystem has also conducted a series of final layout reviews, FLORs, for each of the upper stage structural components. Each FLOR included layout drawings, detailed parts drawings, and a design analysis notebook. Immediately following a layout review, a virtual design review was held, during which the 3D model of the component was reviewed by NDT members and Ares-1 program management by looking at interfaces, clearances, routing, and assembly. These FLORs were critical activities in preparing for the upper stage. The upper stage small solids team is also preparing to conduct the first heavyweight motor test for the ullage settling motor propellant at MSFC. The USM system ensures that ullage is maintained at the forward tank dome during J2X ignition. The system encompasses all functions required to fire the USMs and eject them from the upper stage aft skirt. The purpose of the test is to validate the performance of the USM propellant, propellant grain structure, and propellant geometry for the Ares-1. The heavyweight motor, insulated case, and nozzle are provided by the U.S. Army's Aviation and Missile Research, Development, and Engineering Center, the AMRDEC. After data review and acceptance of the design, fabrication, and checkout of special NASA heavyweight motor tooling is completed and an operations readiness safety inspection is performed, the liner will be applied to the insulated case, and final cast, cure, and finished propellant grain will occur. The motor is then installed in the MSFC test stand for static test firing. Using MSFC thrust stand and data acquisition system, vital performance data will be obtained for the USM propellant design. The first hot fire test of the USM igniter was recently conducted in MSFC Test Stand Area 116. Test results showed that the igniter trace was on target and the igniter is extremely overbuilt. Due to the life cycle phase of the project, this was good news for the team. Future testing will involve an additional 22 igniters being made by Sierra Lobo and to be delivered to MSFC. Other upper stage subsystems are also involved in the rigorous testing and analysis as the element proceeds to PDR. These include thrust vector control hydraulic breadboard testing, reaction control systems RCS water hammer testing, and main propulsion system cryoregulator testing and bench testing of Saturn components. In the early days of the Saturn era, President John F. Kennedy was fond of paraphrasing the Irish writer Frank O'Connor by saying, quote, "This nation has tossed its cap over the wall of space, and we have no choice but to follow it," unquote. As NASA celebrates its 50th anniversary in 2008, the United States again finds itself on the cusp of another glorious era in space exploration. To accomplish its goals, the Ares-1 team must build beyond its current capability to ferry astronauts and cargo to low Earth orbit. And to reach for Mars and beyond, the team must first reach for the Moon. The NASA and Boeing upper stage teams are now integrated, working together and making good progress. They are designing and building the Ares-1 upper stage by using extensive lessons learned to minimize cost, technical, and schedule risks. Today, this nation, like the space pioneers of the 1960s, has once again tossed its cap over the wall of space. We have no choice but to follow it. The Ares-1X vehicle used in the test flight was similar in shape, mass, and size to the planned configuration of later Ares-1 vehicles, but had largely dissimilar internal hardware consisting of only one powered stage. Ares-1 vehicles were intended to launch Orion crew exploration vehicles. Along with the Ares-5 launch system and the Altair lunar lander, Ares-1 and Orion was part of NASA's Constellation program, which was developing spacecraft for U.S. human spaceflight after the Space Shuttle retirement. Ares-1X was the only test flight of a launch vehicle like the Ares-1. The test flight objectives included demonstrating control of a dynamically similar vehicle using control algorithms similar to those used for the Ares-1, performing an in-flight separation staging event between an Ares-1 similar first stage and a representative upper stage, demonstrating assembly and recovery of an Ares-1-like first stage at Kennedy Space Center, demonstrating first stage separating sequencing and measuring first stage atmospheric entry dynamics and parachute performance, characterizing the magnitude of integrated vehicle roll torque throughout first stage flight. The flight also had several secondary objectives, including quantifying the effectiveness of the first stage booster deceleration motors, characterizing induced environments and loads on the vehicle during ascent, demonstrating a procedure for determining the vehicle's position to orient the flight control system, characterize induced loads on the flight test vehicle while on the launch pad, assess potential Ares-1 access locations in the VAB and on the pad, assess first stage electrical umbilical performance, The Ares-1X flight profile closely approximated the flight conditions that the Ares-1 would expect to experience through Mach 4.5 at an altitude of about 130,000 feet or 40,000 meters, and through a maximum dynamic pressure, max Q, of approximately 800 pounds per square foot, 38 kPa. The Ares-1X flight profile resembled the uncrewed Saturn I flights of the 1960s, which tested the Saturn propulsion concept. By flying the vehicle through the first stage separation, the test flight also verified the performance and dynamics of the Ares-1 solid rocket booster in a single stick arrangement, which is different from the solid rocket booster's then current double booster configuration alongside the external tank on the Space Shuttle. Delays in the Ares-1 development schedule due to budgetary pressures and unforeseen engineering and technical difficulties would have increased the gap between the end of the Space Shuttle program and the first operational flight of Ares-1. Rollout of Ares-1X at the Kennedy Space Center Launch Complex 39, secured by 4 bolts on a mobile launcher platform. The Ares-1X vehicle consisted of a functional 4-segment solid rocket booster SRB stage, a 5th segment mass simulator, an upper stage simulator which was similar in shape and heavier than the actual upper stage, as well as a simulated Orion crew module and launch abort system. Since the actual upper stage hardware could not be produced in time for the flight test, the upper stage mass simulator allowed the booster to fly approximately the same trajectory through the first stage of flight. The USS and the CMLAS mass simulators launched by the Ares-1X were not recovered and fell into the Atlantic Ocean. The first stage, including the 5th segment mass simulator, was recovered to retrieve flight data recorders and reusable equipment. The 4-segment solid rocket motor and aft skirt for Ares-1X was drawn directly from the Space Shuttle inventory. The motor was manufactured by ATK Launch Services of Promontory, Utah. The new forward structures were manufactured by Major Tool and Machine of Indianapolis, Indiana. The first stage element was managed by Marshall Space Flight Center in Huntsville, Alabama. Modifications to the solid rocket booster include: the aft skirt was modified to include 8 booster deceleration motors, which pulled the booster directly away from the upper stage simulator, as well as 4 booster tumble motors, which caused the booster to tumble horizontally to decrease its velocity prior to re-entry. The aft skirt also housed one of 2 redundant rate gyro units, which provided data to inform the fault-tolerant inertial navigation unit of the vehicle's attitude and position. Steel ballast of 3,500 pounds, 1,600 kilograms, was also added to the aft skirt to move the first stage center of gravity aft to ensure that the first stage would tumble properly after separation. An extended linear shape charge for the flight termination system to to cover all 4 segments in the event the stage needed to be self-destructed. Cabling for additional pressure and environmental instrumentation. A 5th segment simulator which allowed the Ares-1X to simulate the length and mass of the Ares-1 5-segment motor and housed the first stage avionics module. The FSAM contained the electronics boxes that captured and stored flight data for recovery after splashdown, provided electrical power for the avionics systems, performed separation and parachute deployment commands, contained video cameras that record the first stage separation, a hollow forward skirt which simulated the Ares-1 first stage forward skirt, a forward skirt extension which housed new, larger parachutes. The 3 main parachutes each had a 150-foot, 46-meter diameter, compared to the shuttle booster main parachutes, which are 136 feet, 41 meters across. It also had a shuttle booster heritage nose cap that covers the pilot and drogue chutes. Jettisoning the nose cap released the pilot parachute which pulled out the drogue. The forward skirt extension separated from the booster deploying the main parachutes. A frustrum, which was a hollow inverted half cone that connected the 12-foot 3.7 meter diameter first stage to the 18-foot 5.5 meter diameter upper stage simulator. For the Ares-1X flight test, the frustrum and forward skirt extension were made of aluminum. The forward skirt and 5th segment simulator were made of steel. The upper stage simulator, USS, was manufactured by NASA personnel at Glenn Research Center in Cleveland. Because of transportation limitations, bridge heights on the highways and rivers, the simulator was built out of 11 steel segments, 9.5 feet, 2.9 meters tall by 18 feet, 5.5 meters wide. The USS simulated the shape, mass, and center of gravity characteristics of Ares-1 from the interstage to the top of the service module of the Orion Crew Exploration Vehicle. The centers of mass for the liquid hydrogen and liquid oxygen tanks were simulated through the use of steel ballast plates. The USS included a variety of temperature, vibration, thermal, and acoustic sensors to collect the primary data needed to meet the mission objectives. It also housed the fault-tolerant inertial navigation unit, which controlled the vehicle's flight and primary avionics functions. For stability, the FTINU was mounted on the underside of the lower ballast plates. Ground operation personnel accessed the FTINU through a crew hatch on the side of the interstage segment, which also housed the roll control system. Each USS segment included a ladder and a ring-shaped platform to allow access to the sensors and cabling for the developmental flight instrumentation. The stairs and platforms were necessary because Launch Complex 39B is not tall enough to provide crew access to the upper parts of Ares-1X. The Active Roll Control System, ROCS, was needed because the flight test vehicle had a tendency to roll around its axis of forward motion. The ROCS for the Ares-1X consisted of two modules containing engines originally used on now decommissioned Peacekeeper missiles. The ROCS performed two primary functions: rolling the vehicle 90 degrees after liftoff to emulate the Ares-1 roll attitude at launch, maintaining a constant roll attitude during ascent up to stage separation. The ROCS modules, placed on opposite sides of the outer skin of the upper stage simulator, used hypergolic monomethyl hydrazine MMH and nitrogen tetroxide NTO for propellants, and each included two nozzles, which fired tangential to the skin and at right angles to the roll axis in order to provide a controlling roll torque. The propellants were loaded into the modules at Kennedy Space Center's Hypergol Maintenance Facility, HMF, and transported on the ground for installation into the USS in the Vehicle Assembly Building prior to rollout to Launch Complex 39B. The ROCS modules were designed and constructed to fit into the interstage segment of the USS by Teledyne Brown Engineering in Huntsville, Alabama. The engines were hot fire tested in White Sands Test Facility in 2007 and 2008 to verify that they could perform the pulsing duty cycle required by Ares-1X. At the top of the Ares-1X flight test vehicle was a combined Orion crew module and launch abort system simulator, resembling the structural and aerodynamic characteristics of Ares-1. The full-scale crew module is approximately 16 feet or 4.9 meters in diameter and 7 feet or 2.1 meters tall, while the launch abort system is 46 feet or 14 meters long. The crew module launch abort system simulator was built with high fidelity to ensure that its hardware components accurately reflect the shape and physical properties of the models used in computer analysis and wind tunnel tests. This precision enables NASA to compare CMLAS flight performance with pre-flight predictions with high confidence. The CMLAS simulator also helps verify analysis tools and techniques needed to further develop Ares-1. Ares-1X flight data were collected with sensors throughout the vehicle, including approximately 150 sensors in the crew module launch abort system simulator that recorded thermal, aerodynamic, acoustic, vibration, and other data. Data were transmitted to the ground via telemetry and also stored in the first stage avionics module located in the empty fifth segment. Aerodynamic data collected from sensors in the CMLAS contribute to measurements of vehicle acceleration and angle of attack, how the tip of the rocket slices through the atmosphere is important because that determines the flow of air over the entire vehicle. The CMLAS splashed down in the ocean along with the upper stage simulator after the boost phase of the mission. This simulator was designed and built by a government industry team at Langley Research Center in Virginia. It was flown to Kennedy Space Center by C-5 transport and was the last piece of hardware stacked onto the rocket in the vehicle assembly building. Ares-1X used avionics hardware from the Atlas V Evolved Expendable Launch Vehicle to control its flight. This hardware included the fault-tolerant inertial navigation unit and redundant rate gyro units and cable harnesses. The first stage was controlled primarily by heritage hardware from the existing Space Shuttle systems. A new electronics box, the Ascent Thrust Vector Controller, acted as a translation tool to communicate commands from the Atlas-based flight computer to the solid rocket booster's thrust vector control system. Ares-1X also flew commemorative payload. 3 shoebox-size packages were affixed inside the 5th segment simulator of the first stage to carry 3 DVDs with 60-second home videos recorded by the public and submitted through NASA's website. 3,500 flags to be distributed to Ares-1X team members.